introduction to tree with example. Here we have a circle colored with yellow. This is a node. These are other nodes which are linked among themselves. A node may have a predecessor, or commonly called parent, and may have successor, which is commonly known as child. So if you consider this node here, then this node is having a parent here and two children, this one and this one. In the structure, you can clearly see that between a pair of nodes, you have only one option for connecting those nodes. For example, if you want to connect this node with this node, then you have a link like this. This one is the link from here to here and from here to here. So if you want to move from this node, which I call source as S, and this is your destination D, then from S to D, you have to move through this link only, right? Via this node. From D to S, you have only one way if you want to get back, but there is no other way through which you can move from D to S. If I have a connection from this node to this node, then we find another way through which we can move from D to S, through this link, right? If it happens like this, then it forms a cycle. Please remember that if there is a cycle in this kind of structure, then it is a graph. And in a graph, if there is no cycle, then we call that graph as tree. So tree is a special type of graph that has no cycle. Clear? Now this yellow node is called root. The green ones are called intermediary nodes, and the blue ones are called leaves. Now, how will you identify whether a given node is a root or intermediary node or leaf? Because in a tree, there will be no color. Now let us look at the root. It has three children: child 1, child 2, and child 3. But it does not have a parent or predecessor. You see that? Here is a null. That means no predecessor or no parent is there with this node. So whenever you find a node with no parent or no predecessor, then you call that node as root. If you have a node with no children, but it has parent, then that node is a leaf. So you can see that these blue nodes here are without children, but they have got one parent there, right? And in case of intermediary nodes, they both have a parent and at least one child. This is called level, more specifically level 0. In level 0, we have one node and that is your root. This is level 1 and we have 3 nodes there. In level 2, we have 6 nodes, and in level 3, we have 6 nodes. If you consider the whole structure as a single tree, then you have your root here and we call that tree as T. If you consider this portion only, then this is a subtree of the tree T. We name the subtree as T1 and we have a root here of T1. So regarding T, we have this node as an intermediary node, but regarding T1, which is a subtree of T, we have this node acting as a root. The same thing goes with other subtrees like this. Now question may arise that if I consider this portion only as a subtree, can I do that? Yes, you can do. And you name this subtree as T4, then your root will be here. So this node is an intermediary node regarding T1 as well as T, but regarding T4, this intermediary node becomes a root. So you may consider all the nodes as a root of some subtree, right? This is quite interesting. Now throughout our course, we will concentrate on binary tree. So in this figure, you see a binary tree. How will you identify a binary tree? Look here for the properties. A binary tree will have a root R, which is a distinguished node. That means there will be no other root here. So we have this R here. So we agree with the first property. Second property, if T1 is non-empty, then its root R1 is a left successor of R. What is the meaning of this? Consider this one. This one is a left subtree T1 whose root is this one, right? This one is a left successor of R. You can see that. So this becomes R1, the root of T1, and this node is a left successor of R. So if the left subtree is non-empty, that means T1 is non-empty, then it goes like this. If T2 is non-empty, then its root R2 is a right successor of R. Now this node is a right successor of R and it is non-empty. So this right successor becomes the root of the right subtree T2. The same thing goes with the other subtrees. You can verify that by your own. Now this is the last property you should have. Any node, whether it's a root, it's an intermediary node or leaf, they can have 0, 1 or 2 successors. For example, this root R is having 2 successors, right? Or 2 children. This node R1, this is also having 2 children. R2 having 2 children. This intermediary node also having 2 children. And this leaf is having 0 children. This intermediary node, 2 children. Leaf, 0 children. This leaf, 0 children. This leaf is also having 0 children. And this intermediary node is having only 1 child, right? Then this leaf is having 0 children. And this leaf also having 0 children. Since this structure follows all these properties, then we say this structure is a tree, and more specifically, it is a binary tree. Between these two nodes, we have an edge, that is the connection between any adjacent nodes we call edge, and we name this edge as E1. This is also an edge, we name it E2, this is E3, and this is E4, and you can name the other edges here. This is a definition of a path. It's a sequence of consecutive edges. Remember this word, consecutive. So for example, you may have path P1 as E1, then E2, then E3. See here. This is a path P1. For path P2, we have E1 and E2. So it goes like this. E1 and E2. We may also have path P3 with E2 and E4 like this. What is a branch? Any path, it may start from anywhere, but if it ends to a leaf, then we call that path a branch. Here we have P1, which is ending with E3, and E3 actually ends at this leaf. So path P1 is a branch. Similarly, for path P3, we have this edge E4, which is ending at this leaf. So we have this path as branch. But this path P2 is ending with E2, and E2 ends over here. So this is not a leaf. So P2 is not a branch. What is a depth or a height of a tree? This is determined by the highest node count in a branch or branches. That means you go through all the branches throughout this tree, identify the branch with the highest node involved, count it, and declare that that is the depth of the tree. So let us determine the height or the depth of this tree. So we have branch here. See, this path is ending to this leaf, and we have node count as 4. So this is 1, this is 2, this is 3, and this is 4. For this branch, we also have the node count as 4. For this branch, we have 3 node counts. For this branch, we have 5 node counts. For this one, we have 4. And for this one we have 3. The highest node count here is 5. So we have our depth as 5. Clear? What is a complete binary tree? Here are the properties. Each level, except the last, will have the maximum node count according to its capacity. Now see, this is level 0 and the capacity is 1 and we have only one node. In this level 1, we have capacity 2. These are the 2 nodes. In level 2, we have capacity 4 and we have 4 nodes here. So up to this tree structure is following the first condition. Now if it happens like this, that at level 2 the capacity is 4 but we have 3 nodes, because this is a valid binary tree, the definition allows 0 children, 1 child or 2 children. So here this node is having 1 child. So it's following the property of binary tree. So it is a binary tree, but it is missing 1 child on the right hand side, and with this situation it is having another level here. So this is not the last level, but the property says here that except the last level, whatever levels are there, each level must have a maximum node count according to its capacity. So it is violating the first property, right? So you must include the leaf here or any other node. Now we move to the second property, which is talking about the last level. The last level goes like this. This is level 3 and it has a maximum capacity of 8 and we have only 5 children. Now what our property says is that you may have lesser node count than its maximum capacity. So our structure is still following the property, but there is a condition here. If you have lesser node count in the last level, then there should be no missing children before the last child. Now what is the meaning of this? This is the last child. Before this last child, you can see that there is no vacancy for any children over here. These 2 children over here are full. These 2 children here are full. So this structure follows all the properties, right? Now if it goes like this, so where is the last child? This one, right? But before this last child, there is a missing link here. This is not allowed. So the structure must look like this. So this is a complete binary tree since we have followed all the conditions here. This is the formula for computation of depth of a complete binary tree with n nodes. This is a lower ceiling log n base 2 plus 1. You input the node count here and you get the depth. In the next video, I will show you how to express a binary tree in algebraic form. Thanks for watching and take care.